Welcome to the third instalment of our Retrofit Knowledge Exchange series, and this is the second collaborative event between the Scottish Ecological Design Association and CIAT Scotland East Region. So, as part of our Retrofit Knowledge Exchange session, today's instalment will follow on from our last three retrofit webinars. So last week, our speakers explored the retrofit methods for an A-listed building and a 4 and a block archetype using conservation methods, deep retrofit and plot renewal. Yesterday, we explored the use of mass timber in conservation and preservation of existing buildings. And today, our speakers will be exploring Enerphit as a retrofit method and applying that to the multi-storey flat archetypes. So now I am proud to welcome speakers from LMA Architects, Collective Energy and Collective Architecture. Both practices have a strong culture of sustainable design and promoting the architectural technology discipline. Our speakers today have a long and very successful career of applying energy efficiency retrofit solutions to existing buildings. So today they're joining us to share their knowledge on applying the principles of Enerphit as a retrofit methodology. So first off, we will have Natasha, an associate from LMA Architects and a director for the Scottish Ecological Design Association. She is introducing us to the principles of Enerphit and its role within sustainable architecture and retrofit. Rupert, an architect and passive house designer at Collective Energy and Collective Architecture, will be describing how he and his team have applied those principles to achieve mass retrofit. And then wrapping us up today will be James, architect and passive house designer, again from Collective Energy and Collective Architecture, and he'll be describing the future of Enerphit as a retrofit tool. That's not correct. He'll be describing the ideas and approaches to meet net zero for retrofit projects. So, Natasha, if you are ready, please steal the screen from me and start when you're good to go. I'll let you know when you've got. Yep, you've taken it from me. That's good.
Thanks, John. Good afternoon, everybody. Hi, I'm Natasha from LMA Architects. I'm a director of the Scottish Ecological Design Association. I just wanted to start by giving a wee introduction to the Scottish Ecological Design Association, if anyone's not familiar with us. We are a Scottish charity. We've been around for 30 years. We raise awareness of good ecological design and how design affects health and well-being. We do this by essentially spreading information. We have loads of stuff on our website. We do issue publications, we do seminars, we have a quarterly magazine. Also, we have quite a few design guides on our website. If anyone's interested in downloading these are free for everybody to look at. We've a new one coming this year on indoor air quality, which is going to be really good. And just on retrofit, the idea of retrofit, I would encourage everybody to download Chris Morgan's Sustainable Renovation Guide. That's a really good document if anybody's not read that. So John's asked me to introduce Enerphit. I'm just going to go through the basic principles and have a wee look at its role in sustainable design and retrofit, obviously. So what is Enerphit? So I presume most people will be aware of the Passive House concept. The Passive House Institute is an independent research institute. It's also been around for 30 years. So this is not a new concept. The Passive House concept is for new build construction. And this is an internationally recognised performance-based energy standard for new construction. The Enerphit standard is the equivalent Passive House standard for certified refurbishments of existing buildings. It uses the PHPP software that we use for Passive House design. And there are three kind of levels. There's classic, plus and premium. So depending on what standard you want to reach. This wee table on the left here just gives you an idea of the difference between Passive House and Enerphit. I'm not going to run through all the numbers, but there isn't a lot of difference. It's a very onerous standard to meet. I think Enerphit's probably more difficult to meet than Passive House, but the two main differences are in the space heating demand and this line here, and air tightness. But you can see air tightness, we're looking at 1 air change per hour as opposed to 0.6, so really still quite an onerous standard. So I just also wanted to mention there is an Enerphit Retrofit Plan, which is a really useful thing. If, say, if you have a client that's looking towards 2045, how do they get their buildings down to meet the energy targets? But this is a step-by-step retrofit plan that at the end of the day you end up with an Enerphit certified building, but you conceive a plan whereby you're not doing abortive work. You don't have to go back and redo insulation. So I think that's just a good thing for everyone to be aware of in relation to Enerphit. So why do we need to retrofit? Why do we need things like Enerphit? Obviously, everybody's aware of the 2045 net zero targets. Most of our buildings that we have just now will still be around in 2045, so we need to work with them and get them down to the standards that we need in terms of reduction of CO2 emissions. Another massive driver for me is to make our buildings healthier for people to live in. It's quite a shocking statistic that nearly a quarter of Scotland's population are in fuel poverty, and this is largely because the buildings that they live in are leaky, they're cold, the heating systems are expensive to run. So for me, there's really a dual aspect of doing retrofit projects. So what are the key issues with retrofit, and why would we use Enerphit? So I think with a retrofit of existing buildings, we need to understand the risks of what we're doing, because whenever we go in and mess with an existing building, there are risks, and these risks affect the building and the occupants. And that's why it's really important to have approach the building as a whole, and then we obtain a balance between energy efficiency, the comfort and health of the occupants, and the durability of the building fabric. That obviously has to be balanced with cost, which I'm not really going to talk too much about today. So really with Enerphit and retrofit, you're looking at an individual building approach, or an individual typology approach perhaps. Enerphit's appropriate for this because it is a tried and tested methodology. So it's important that we understand that what we do is actually making a difference, and it's not just a kind of patch job, and we don't really know if it's doing any good. So I think Enerphit's and Passive Houses, it's been going for a while. If you go into the Passive House website, you can have a look at case studies where houses or buildings have been monitored, and you can see that the objectives of the PPHPP are actually being met by the buildings through their lifetime. I just want to mention maintenance here briefly as a risk. I think when you first go and look at an existing building, you need to assess how well it's been looked after. There's no point putting in lots of insulation if the roof's leaking. And likewise, at the end of the day, it's important to leave clients with a maintenance regime so they know how to look after the building and keep all the good work going well. Anyway, so what is Enerphit? What are the criteria for Enerphit? The Enerphit follows all the same principles as Passive House, as I showed you in that first slide. So the actual principles are improved thermal insulation, minimising thermal bridging almost to down to nothing, low air tightness, good quality windows, mechanical ventilation with heat recovery, and all this brings about very low heating demands, and we would be looking to use renewable energy sources and renewable products. So I'm just going to give you a few of my thoughts on a few of these sections. When we insulate buildings, we have to look at the risks again, and obviously when we insulate buildings, we can change the way that moisture moves through them. All buildings have solid walls potentially. Moisture can move quite freely through an old stone wall, but if we have a new building with a cavity wall, you see what moisture coming in as far as the cavity and then being expelled that way. So you really need to assess the building and see what the risks are in relation to moisture. The most efficient way to insulate an existing building is externally, but obviously that's not going to work for every building. If you've got an A-listed conservation building in the middle of Edinburgh, you're not going to insulate it on the outside. So there's issues like that. If you're looking at insulating internally, we have to think about space requirements and loss of features and how we detail around all those fiddly junctions. From an ecological perspective, I'd encourage everybody to think about the types of insulation you're specifying. Obviously, I'm a keen user of natural and breathable building products. These generally have lower embodied energy. They're largely vapor permeable, so they allow vapor to move through them. Sometimes they can store vapor and release it later. And statistically also, they are usually made of less toxic chemicals, so there's less chemicals that build up in your buildings later on once they're constructed. Just as a kind of costing thing, it's generally cheaper to insulate roofs and floors as compared to walls. So if you're, if you've got your Enerphit calculations not quite working, maybe look at beefing up the roof insulation. That's a kind of easier one to look at. So thermal bridging is the next criteria. This for me, I think, is the most difficult one. And I think this for me is probably the one that will determine whether you can meet Enerphit or not. Enerphit won't work for all projects, but it will work for a lot of projects. So obviously existing buildings have thermal bridges already in them. And as we work towards, if you increase the insulation and the air tightness around the building, if you don't deal with the thermal bridging, also you will accentuate the heat flow out through these junctions and increase the risk of causing condensation and mold in these locations. I've put a wee picture here. This is obviously a stone wall with some timber joists going into here, just to give you something to think about. How would we insulate that? How would we do that to meet Enerphit standards? So if we just put insulation around the ends of the joists here, we run the risk of trapping moisture in the timber, and then that might decay over time. And we're not creating a continuous line of insulation. Another method might be to go in and cut each joist end and insert insulation up behind it and then hang the joist off joist hangers. So again, it's very much a case-by-case situation. So the next aspect is air tightness. And again, just thinking about this whole building approach, the more we insulate, the more we eliminate thermal bridging, we also need to look at air tightness. And I think it's looking at all these things together rather than as separate items. Air tightness, again, is a cause of drafts in a building, so it can cause quite considerable discomfort for the occupants. But it is a key factor for reducing heat loss. Just put a product here. I'm not here promoting products, but there are products out there that can create air tightness layers but still allow vapor to move, and they're really good products to use. And just something that I've learned is always check the product testing of air tightness products, because not all manufacturers will give you testing, so you don't actually know if they can achieve these lower air tightnesses. So it's just something to be aware of. So in relation to windows, obviously most passive house projects require triple. They don't require triple glazing, but generally we need to put triple glazing in to meet standard. And again, this is about completing the building envelope. So if you put in triple glazing, you'll find that the inner pane of glass on a triple glazed window is a couple of degrees warmer than with a double glazed window, which will then help eliminate drafts in the building. And you won't have to do things like put radiators under the windows to improve comfort. I mentioned here the component database. So if you go onto the Passive House website, there is a component database, and Windows are a good one. You can just go in and pick products that have already been certified. Now, for Passive House and Enerphit, you don't need to use certified products or Windows, but it's an easy solution. Obviously, this window that I've shown here wouldn't be suitable for all projects, particularly conservation projects. So again, it's a different solution for different projects. On a kind of cost and energy efficiency perspective, just being mindful of how many windows that you need to open. The more opening windows you'll lose points in your PHPP software, and also they cost more money. So if you don't need to have 4 opening windows in a room, for example, maybe reduce that to 1, and that'll help you get towards the objectives of the software. In terms of materials, there's a timber window shown here. Timber is generally recognised to be a renewable product, whereas products like UPVC and aluminium require energy to make them and quite often give off pollutants. They can both be recycled though. So lastly, just on MVHR, along with moisture movement, ventilation is a key risk, I think, in Enerphit projects and any retrofit projects, which is why Enerphit requires the use of an MVHR system. And this also dramatically cuts energy use and carbon dioxide emissions. I think it's pretty much a no-brainer that extract fans just bring in cold air, so they're not very sustainable. Whereas an MVHR system brings in fresh air and preheats it using the exhaust air, the warm exhaust air that's being extracted. Along with removing moisture, an MVHR will also remove pollutants in the building. So hopefully we can all work towards using more less polluting products in our building, but it's really important in airtight buildings to remove pollutants, so because they affect people's health. Moisture obviously affects people's health and building health. From a practical point of view, with regard to retrofit, you need to think about where the ducts run. This is obviously a small house here, but in a larger building, it can be quite challenging to figure out where all your ducts are running. So just to conclude, why do we need retrofit? We need retrofit to reduce carbon dioxide emissions so we can get to net zero, but equally importantly, we need retrofit so we can make our buildings healthier for people to live in and work in and play in. Enerphit, I think, is a good model for this. It won't fit every existing building, but it is a tried and tested methodology. So if you can achieve that, you will know, you'll get what it says in the tin. So I think that's why it's a good methodology to look at for retrofit. And that is me. So thank you very much, and I will pass you over to Rupert.
Thanks. Afternoon, everyone. Apologies first off if some of you have probably seen a number of these slides before. It's been in a couple of other presentations that I think just on the list that's here, I think a few of you have attended. Okay, so Woodside multi-storey flats in Glasgow. Next slide. Starting with why we've gone down passive house. There were a number of reasons, but fundamentally what it means to the design team is it allows us to engage with the building design and have informed discussion with the client and the design team around how best to optimize the energy efficiency of the building to achieve low energy demand and high levels of comfort for the residents. Principles, I won't go into this in detail because Natasha's really covered it, but there's really 5 principles of passive house, which are for Enerphit and the new build, being glazing, insulation, air tightness, thermal bridge free construction, and mechanical ventilation with heat recovery. Essentially, just briefly again, what we're trying to do is retain the heat for longer. So we've got a thermos on the left-hand side and a cafetiere on the right-hand side. Both keep the fluid warm. One just retains the heat and keeps it warm. The other one needs constant energy input. So the cafetiere is what we're trying to avoid, and the thermos is what we're trying to achieve. The why passive house on this project? Well, dual reasons. Primarily it emanated from mitigating fuel poverty. And also a requirement to meet energy efficiency EIS standard social housing in Scotland. It seems to be the best solution in terms of tried and tested and robust for achieving these goals. The climate emergency has obviously come to the fore, and we're recognising that 80% of the homes that we live in today will still be here in 2050. So the retrofit is the big item that we need to address. We can achieve extremely low heating costs. Space heating is what we're referring to, despite rises in energy prices. High levels of comfort. We can help protect the building, mold-free, reduce moisture damage. These buildings had a lot of black mold in them prior to the works being carried out. High quality fresh air throughout, so we're not achieving energy efficiency to the detriment of air quality for the residents, and just generally a radically improved indoor environment. The Passive House Standard has various quality assurance processes and third-party verification of that with a Passive House certifier in the process. So that it's the methodology. Achieving Enerphit is maybe the aspiration and the target. What I'd like to message in this presentation is actually the methodology is the most important thing. Even if you're not going to be able to achieve the actual certification, you're going to have a much better building by following the methodology than you would if you simply revert to minimum compliance requirements. There's a lot of gaps in the compliance software, which means that you don't have the important conversations with the design team, and you get that performance gap, which we're aware of in the industry, in what's been designed and what's been built. For this one, the choice is Enerphit, and we had to meet each, but with the client, which is Andy Woodburn, who I think is here as well at the time, looking beyond the minimum compliance at the long term, because the buildings are going to be here for a lot longer than just simply the next iteration of an energy standard. We're looking for it for the life of the building. Enerphit has a stepwise option as well, so the retrofit plan that Natasha discussed. You can set the plan, do the full model of from the outset, and look at how you can actually implement it over a period of time. That will depend on each project and its typology. A lot of the work that we were doing to these buildings, primarily external, with the occupants staying in place throughout the construction works. But it makes sense when you're investing in the scaffolding or the mast climbers for 22 stories to tackle all of these things at the same time. So most of these external works have been carried out all in the one contract. One of the principal reasons we pitched the Enerphit standard against other available grants and funding opportunities, and found out that to achieve the grant funding, you needed to do a minimum amount of fabric improvement in any case. So we would have been doing the external wall insulation to achieve some other grants funding and things. So it just made sense to do it right rather than just do a half measure. So essentially, it was the first step in a sensible way towards net zero and achieving future grant funding. And it just makes sense. You know, there's no point in getting lots of grant funding for renewable energy or renewable heat incentives, renewable technology, and putting it on a building which is just losing the energy as quickly as it's being generated. The principles, Passivhaus principles, the perception versus the reality. I think when we first looked at this, it was early on in the Passivhaus career, and had been looking at more smaller scale domestic housing, and thinking, right, okay, well, we're going to need a lot of insulation, but the key element in this is the actual scale of the buildings and the form factor, and the form factor overrides a lot of the other elements in terms of how much insulation you're going to need. So on a one-off domestic house, you might be having wall thicknesses of about 500 to 600 mil overall. On this, in terms of the insulation thickness, we've only put 120 mil of rock wool on the wide elevations, and we added a little bit more to the gables. So those flats, which had slightly more thermal envelope, were compensated. We looked at minimizing the thermal bridges wherever possible and calculating any residual losses that were there. The orientation's pretty much fixed, but we had to be mindful of solar gain and potential for overheating. MVHR, mechanical ventilation with heat recovery, looking at an individual dwelling solution, primarily with the retrofit, trying to fit in a communal system. The complexity of that with the existing structure was discounted quite early on. And then the air tightness, we did some initial testing on the buildings before we did any retrofit work, and found out that they were inherently good in comparison to current building standards. So we were down at an air permeability rather than air tightness from Passivhaus of around 5, which is pretty much what a lot of the new builds are still getting built to. There was room for improvement. So just looking at the form factor here, there's a diagram which essentially shows you the relationship between heat loss area, or the thermal envelope, and the amount of insulation that you're going to need. So you have the heat loss area, you have the amount of insulation as a general rule of thumb. So you're squaring off, not squaring the circle, but squaring the square. If you've got lots of projections and recesses, you're adding a lot of thermal envelope. And if you can actually make that more streamlined, then you can reduce the amount of insulation that you're going to need. So whilst the blocks were already very high sort of efficiency in terms of the thermal envelope, there was room for improvement. We had historically recessed balconies on approximately half of the flat types and projecting amenity balconies on the other half. By bringing the recessed balconies within the thermal envelope and taking the triple glazing to the outside of that balcony, we reduced down the thermal envelope by around 20%, which was quite considerable considering the size of the buildings. The projecting amenity balconies were an inherent thermal bridge. We did look at one point at just removing them. They didn't seem to be getting that much use, but there was some surveys and consultation and decision made to retain them, which I think in the long term has been an asset, because these winter gardens, which we've put on the balconies instead, are getting a lot of use by the residents and are probably the favourite feature. To mitigate the thermal bridge of the slab, which is part of the structural slab projecting out, we've wrapped it in insulation, so we'll come to that bit in a little while. During the contract, when putting in these winter gardens, there was a requirement to add more structure in to support the roof canopies, and introducing steel to support the actual structure creates its own complications with thermal bridges. So the outriggers here go directly into the floor slab, but we have isolated the thermal bridge with 50mm structural thermal packers or thermal breaks. But you can see that it creates a bit of a complex junction for air tightness as well. We've had to seal that area up and use the 50mm depth of the actual isolation packer to its benefit for the air tightness strategy. The air tightness, as I'd said before, the large square here was the original leakage rate at the air pressure air test at 50 pascals. And that's equivalent to 21 centimeters, or the width of an A4 piece of paper square. The absolute threshold for Enerphit is these smaller dotted square, which is about the size of a post-it note. And then the target for passive house for new build is smaller than that again. So there is quite an improvement still required. And the methodology that we use for that, just taking a slightly more pragmatic approach, is to utilize the inherent air tightness of precast concrete and seal up the joints in the actual concrete panels with a foam backer cord and a flexible mastic to seal the actual joint. So we did quite a lot of research into the performance of the actual mastic as well to be used there. There's also, and this is quite a large heat loss area, but you've got these small white dots of mastic, which were actual drainage slots in the precast panels. So that's wind was previously blowing straight into the apartments. And the only thing going from there into the apartment was a layer of plasterboard. So that's why everyone complained of drafts previously. There was value engineering required. When we went out to tender, we went beyond what we knew the budget would be, but we were mindful that if there was value engineering, we didn't want to compromise the fabric first approach. So the things that were removed were the add-ons, the renewables. So we had a communal solar thermal air source heat pump and distribution for heating and hot water, and that got removed out to meet the budget, which wasn't a huge loss in the grand scheme of things. And then we also had to look at some of the thermal bridges, which were adding on quite a cost to try and resolve. In the process, to meet the contract, the actual requirement to meet certification was dropped because we were in PHPP, which is Passive House Planning Package version 8. It's now currently 9, and version 10 is coming out soon, and there's subtle tweaks with that. But we weren't able to meet the primary energy demand in version 8 without those renewables. But the methodology was to be maintained. Repeatable junctions to resolve. This is a thermographic image of the double glazing that was in there previously. At the outset, the glazing wasn't actually down for replacement. It had about another 12 years before it was in the timeline for when it was to be replaced. But there was sense in doing it bringing that forward, given the time frame for construction, but also the interfacing of windows to the adjacent insulation. And also this thermal image highlighted whilst it might have been double glazed, there was actually quite a lot of poor performance related to it. So, and this is one of my pet hates. This always gets missed in all of a lot of the sort of retrofits that do go on, is how windows are actually joined to their interfaces. And you can see that these windows have been coupled on site, and there's huge air loss or leakage and thermal bridging around the actual coupling points, as well as the trickle vents in the actual windows. The new windows to go in are UPVC, or were UPVC. They're not Passive House certified, so we had to do quite a lot of background checks. We decided to fit out one flat first and test it. Got the air testing pressure fans on so that we could actually make sure that it was fit for purpose. And we found that in the local manufacturing, there was room for not scope creep, but specification change. So the hinges got changed to a slightly cheaper one. And that was actually compromising the air seals in the way that it closed. So by doing the initial air test here, we were able to catch that before it got rolled out to the 304 dwellings. The main working detail that we have here shows the amenity balcony on the west elevation, and how essentially the thermal envelope line is the vertical line where the triple glazing is. The winter garden itself is just a single glazed, unheated external space. But we've had to insulate around the actual projecting slab. And we've taken great care in how the sequencing and the interface of the insulation to get thermal continuity throughout. The top left our chart is what we call the energy balance, and you can get this output from the Passive House Planning Package. And it essentially shows you where all of your losses are and relative to your gains. So just looking into that in a little bit more detail, the red square is your actual heating demand. You can see that to get the energy balance against all of the losses, the internal heat gains from people, from equipment, actually becomes quite a decent proportion, and the solar gains through the glazing almost balance out against the actual losses from the windows over the year. The walls obviously are a major proportion of the thermal envelope, so they're still going to be quite a large element in the actual losses. But it's interesting, even with MVHR, the amount of losses that there are from ventilation. So that would be infinitely greater if we were providing good quality air through just an extract system. At the bottom left, it's just to indicate that grid carbon intensity is on the way down. The red line indicates where gas carbon intensity is per kilowatt hour, and grams per kilowatt hour. And the electricity grid has decarbonized now to a point whereby it's slightly better than gas. So these buildings were originally all electric. They're still all electric. We did take out all of the renewables out of the system, but we're better staying electric in the longer term in terms of reducing the carbon emissions. And because we've gone with such a rigorous energy efficiency standard, even on direct electric, the heating bills should be affordable. Progress external wall insulation. This is the base coat, showing how it's continuous, carefully done even before the amenity balconies are added on. Completion photos. And then I've just got a couple of slides on MVHR. So this was probably the biggest talking point before the contract and during the contract. And obviously at the time, I think it was 2015 when we were originally looking at the designing, planning of this. It wasn't something that was featured that heavily in the social housing market. We went on a bit of a journey to look what other options there might be out there and how we can address some of the concerns. We found a product which didn't have any certification at the time, which was a single room hole in the wall mechanical vent and heat recovery, and had a copper wire heat exchanger which doubled up as a filter. It sounded too good to be true, so we tested it, and it probably was too good to be true at that time. But we worked with them to add on an extract duct. So we were pulling the air from one room and extracting it from all other rooms. And we got certification. We also had with Chris Morgan, I'm not sure if he's here, did about 6 months testing on the unit in the most onerous or trial condition that we could, with a five occupant flat, and we were trying to test it to fail, and I think it was probably borderline at the end. However, we couldn't get into the contract because certification had no certification at the time of tender, and we opted more for a Passive House certified heat recovery unit and system as part of the contract. Unfortunately, during the contract, this got slightly more value engineered, but we managed to maintain the distribution of high quality spiral bound safe seal metal ductwork. And the unit that's gone in isn't a Passive House certified unit, but it was tested by the DIBT, which I think is the Deutsche Institut Baumtech, which the Passive House Institute will recognise the testing. So we didn't get hit with the 12% deduction on efficiency for not using Passive House certified units.
Got 5 minutes.
Okay, brilliant. It's an okay system. It's better than probably most UK installs, but I think there's still room for improvement. And I think that hopefully when the dust settles on the contract, we're hoping to get back in and review. So just finishing up, for Enerphit, I think on this journey of experience, it's I think it's really the first step to true zero, not just net zero. And what it actually allowed us to consider, whilst it wasn't part of the original brief, was what that actually opened up for opportunities. So when you're reducing the energy demand so low, you can start looking for harvesting residual energy from local systems. So we looked at the sewage waste heat recovery, because we've got such a high density of dwellings and the end of the sewage system. There was potential to utilize the waste product from the buildings, and the feasibility calculations for that indicated that would have been enough to meet the residual space heating demand. But there's other things that you can link in as well. So we looked at trying to tackle food poverty as well, with utilizing the circular economy of taking out the double glazing and putting it into community commercial scaled greenhouse. But this was early stages on some thoughts on how we can move on from just Enerphit. And we've started putting that into a project just down the road, actually, at Civic House. So this one's just photos from the scaffold came down at the weekend, and we've used the Enerphit stepwise here. We've got a couple of steps left to do, but we've done all the external wall installation, tightness, windows, MVHR. There's a 50 kilowatt PV array on the roof, and we've kept the glazing aside for a small greenhouse. But we're trying to optimize the self-consumption of self-generated energy. But there will be an energy surplus to the grid as well. So micro power station is, I think, one thing that we're trying to look at. And this is developed onto us setting up collective energy last year, which approximately 20% of our office is now trained as passive house designers. And we have some other skill sets in there for circular economy advisors, and building performance evaluation with specialist testing equipment. So I'll take from there and lead on to James. It's going to take you into net zero.
Hello, everyone. Everybody see that?
Yeah, that's coming through nice and clear, James.
Great. So today I'm going to speak to you a bit about some of the thinking we've been giving to retrofit and how it sits relative to the drive to net zero. But firstly, a little bit of an introduction to collective energy. We set up collective energy in 2020 to offer some key services and advice on how to make buildings, places, processes, and communities more sustainable and effective. We work with our clients, consultants and collaborators to develop their projects, methods, and ideas to be climate neutral, socially sustainable, and holistic. And there's 6 kind of core themes that we use to address this. We look at the social human factor of sustainability, the circular economy, energy, and also carbon, and how the two are related. Really importantly as well, biodiversity and ecology, as well as water ecology, and then travel and how we can get to the places that we want to be, to live, work, and play in a sustainable way. All of this includes the necessary drive to meet net zero carbon, and developing regenerative and circular models to reduce energy demand. And our ethos is to take a fabric first approach and to make sure that all the time we are closing the performance gap. As Rupert said, we've got a strong team. This is actually an old slide. We've now got a few more team members who have joined the collective energy team and become certified. And the kind of scope of our services is passive house design services, circular economy consultancy, and also building performance analysis. So why do we want to retrofit to net zero? I think we can all agree that we are in the grip of a climate emergency, and that we do not have anywhere else to go. So we need to make this world a better place, and make sure that we can do everything we can to keep global temperature rises below 1.5 degrees C, which the Committee on Climate Change has set as a guideline to avoid runaway climate change. The Scottish Government has committed to Scotland being net zero by 2045. The UK government, as I'm sure you all know, set that to 2050. But ambitiously, many local authorities have committed to net zero by 2030. One of the kind of burning questions, and the answer to this is quite often different depending on who you're speaking to, but what does net zero actually mean? In the context of buildings and construction, the UK Green Building Council has produced a very clear and definitive explanation. So as far as net zero carbon is concerned, you've got two categories. The first relates to construction, and that is the emissions that are associated with the buildings product and construction stages up to practical completion, and trying to get those as to zero or negative through the use of offsets or net export of on-site renewable energy. The second is operational energy, and that's defined as when the amount of carbon emissions associated with the building's operational energy on an annual basis is zero or negative. A net zero carbon building is highly energy efficient and powered from on-site and or off-site renewable energy sources with any remaining carbon balance offset. I've highlighted the net zero operational energy because at the moment that's the primary focus, and it relates closest to the work that we need to do with retrofit. So what does net zero mean for Scotland's homes? Our view is that all new housing needs to be designed to be net zero or net zero ready from 2025. If you're going to aim to hit 2030 as a net zero, that it's almost sort of non-negotiable. You really, any pipeline work from 2025 needs to be along those lines. And similarly, even if you're aiming for 2045, you should really be thinking along those lines as well, purely because any homes that are not designed to those standards will need to be retrofitted at a far greater expense than to build in the measures now. So what does that mean standards wise? You're looking at EPC band ratings of A to A+, and Passive House Plus or Premium, and designing to LETI standards, which is the London Energy Transition Initiative guidelines. So what about Scotland's existing housing stock? At the moment, Scotland's got somewhere in the region of 2.4 million occupied dwellings. 36% of those are flats, 22% houses, 23% semi-detached houses, and 90% terraced houses. All that is a mixture of tenure, with the bulk sitting in privately owned properties, and then council and housing association forming nearly a quarter of all of those homes, and 14% rented private landlord. Currently, less than half of Scotland's homes meet EPC C. And so basically just about the majority are EPC band D or worse. And as Rupert has said, and Natasha as well, 80% of these homes will be here by still being used in 2050. So that equates to about 1.9 million homes that need to be retrofitted to get as close to net zero carbon operational energy as possible. So that equates to the scale of the challenge. That if we're going to retrofit all of those homes, we need to basically be doing 211,000 homes a year by 2030, or nearly 80,000 homes per year to meet that challenge by 2045. So I think that those are pretty daunting numbers, it has to be said, but that is the scale of the challenge. A bit of historic context. Post World War I, through the implementation of the 1919 Housing Act, there was a peak in house building right in the 1930s of 350,000 new homes a year. So that equates to about 958 homes a day. This is across the UK. And then in post-war Britain in the 50s, local authorities were building 250 new homes a year, or 685 homes a day. So I'm saying that for context, so that we don't all despair. The challenge is great, but I do say it can be met. Part of what we need to do in our work is to understand the parameters of what we're dealing with the housing stock. This relates to 4 key constraints. The heritage constraints, which are basically, does the property have any listings or conservation status that might affect how we deal with the property and what retrofit approach can be. The building age, because that dictates quite a lot of measures and feeds directly into what the retrofit approach would be, what the building type is as well, whether it's a flat, a house, whether it's end of terrace, mid terrace, whether it's semi-detached or a bungalow, has a guiding factor on what measures can be put in place, and ultimately the construction type as well, with some types lending themselves more to retrofit and deep retrofit measures than others. What are the tools that we can use? As Natasha and Rupert have highlighted already, Passive House and Enerphit are key tools for delivering a deep retrofit and assessing energy performance. Within Enerphit, you have the energy assessment method, as well as an elemental approach. Enerphit can be applied in a step-by-step method to work with funding available to the homeowner or the agency that is responsible, the landlord that's responsible for all of the homes. And recently, the Passive House Institute have been trialing a sort of spin-off of Enerphit, which they're calling Outfit, which is the application of the elemental approach to Enerphit on retrofit at scale to see how we can start to deliver retrofit at scale. Another useful tool is the Acb Retrofit Standard. Past 20 that works and recommends the use of PHPP as energy assessment. Past 2035, 2030 is a new British standard for energy efficiency retrofits. This doesn't set performance standards, but it's an incredibly useful document for outlining the processes that need to be implemented for, particularly for step-by-step retrofit within the industry. CEDA have also produced some really useful publications and guidance, and I'm happy to plug what Natasha was plugging earlier. The Sustainable Renovation Guide is incredibly useful if you are retrofitting older properties. So how do we get to net zero? What we're trying to show in this graphic is some of the relationship between CO2 and energy demand, through our analysis, what we've been looking at is the degrees to which you might carry out whole house retrofits, and we've sort of broken those down into shallow green, mid green, and deep green retrofit tiers, and assigned space heating demands relative to those based on current standards, Enerphit and Acb Retrofit Standards. So at the moment, the business as usual approach, you've got homes that have space heating demands ranging between 150 and upwards of 240. We're really wanting to get energy demand as low as possible because there's a direct relationship between heating demand and your CO2 emissions. The shallow green retrofit is basically looking to get you between 50 and 100 kilowatt hours per meter squared for your space heating demand. Mid green, 25 to 50. So that's getting your EPC band closer to A and also starting to meet EIS 2 compliance. And then deep green retrofit is sort of is Enerphit Standard, where you're between 0 and 25 kilowatt hours per meter squared per year, and your EPC band is somewhere between B and A plus, and depending on your degree to which you apply Enerphit. Enerphit can be applied as Enerphit Classic or Enerphit Premium, where you're effectively generating energy on site to reduce your energy demand. So the other factor within here you'll see in the red is the potential for the grid decarbonization to help you. These are sort of hypothetical extents to which CO2 emissions can be reduced based on some high-level modeling that we've been doing. But currently, the average home is generating somewhere between 3 and 4 tons of CO2 a year. And what we've tried to look at is what would be the impact of each of those retrofit types on making that reduction, factoring in the gradual decarbonization of the grid. So you can see that once you start to undertake your retrofits, you start to become locked into certain performances and more heavily reliant on grid decarbonization once you've carried out your retrofit.
Sorry, James, 5 minutes left.
Sure, I'll rattle through these. We've identified as in line with what PAS 2035 have described in their guidance as a set of step-by-step approach to delivering a retrofit. First step is to carry out an extensive investigative work. The second is to conduct extensive energy modeling, plan your deep retrofit, and then implement your phased energy improvements. And at the end of that, you come back, carry out your testing, commissioning, and monitoring to make sure that the as designed performance is being delivered through the build. Some of the before and after energy modeling that we've been doing is trying to actually understand U values of existing buildings that we've been looking at, what their CO2 emissions are, what their space heating demand is, and then looking at at what that reduction can be. So with some of those, we're able to get as low as as great a reduction as 97%. That's with the application of on-site energy generation, reducing the primary energy demand or reducing space heating demand by significant amounts, all through adopting a fabric-first deep retrofit approach. The advantages of using PHPP as is that it's got a built-in step-by-step retrofit scheduler, and you can, by putting in your maintenance requirements for the building fabric elements, you can start to identify when the optimum time frame for carrying out retrofit work can be planned. So one of the things we've also looked at is the step change improvement that you can get with reducing your specific heating demand, your space heating demand. And the important thing to note here is, compared between, let's say, a shallow green and a deep green retrofit, is that the measures that you take will get you to a point where you will only be able to get so far with a shallow green or even a mid green, and that you're effectively locked in, your performance is locked in for the future. Some of the performance targets we've talked about already. Air tightness is a really key part of that. Shallow green retrofit, we've sort of identified as a guide that is kept below 5. Mid green is below 2, in line with Acb retrofit guidance, and then deep green is Enerphit standard. All the time doing this through the fabric first approach. So as a timeline, thinking about how can we get to where we need to be between now and 2030, I think the next few years we need to carry out our investigation and planning work, establish and expand frameworks, and make sure that pilot projects are being pushed forward. And then from 2024 onwards, we're really pushing for whole house retrofit to be implemented across the nation's housing stock, using fabric first, using on-site renewables, and making sure that we're testing and monitoring performance. And then at the end of that, we're closing the remaining gap, ideally through off-site renewable energy. If that can be linked through direct wire, that's ideal. Otherwise, through carbon offsetting. So some methods for closing that gap. I suppose one of the big questions is, can we just wait for the grid to decarbonize? BEIS have said that at the moment there's almost a quarter of a kilo in every kilowatt hour of electricity, but by 2040 that will be down to about 67 grams. However, relying on electricity to decarbonize is going to put a huge amount of pressure on the national grid, and currently there is not capacity. Even if every home in the nation was retrofitted to passive house standards, not Enerphit, but passive house standards, where your peak heating load is 15 kilowatt hours, that would be taking up almost half of 2050's grid capacity. That's before you factor in things like electric cars and commercial property energy demand as well. So we really need to be focusing on a fabric first approach, reduce energy demand as much as possible before we start to rely on any decarbonization of the grid. And so no half measures allowed. So offsite renewable energy is one way of dealing with offsetting or closing that gap. This is through sustainable heat or an electricity network, a renewable heat or electricity network, I should say. That could also be through private wire to a local dedicated offsite renewable energy source. Or alternatively through renewable energy suppliers, of which there are only 3 properly renewable energy suppliers in the UK. Green leases are an option for commercial properties, but you need to bear in mind that you need to demonstrate an additionality if you're using renewable energy suppliers, and also need REGO certification for the supply. Offsetting is, I suppose, the stopgap. It should never be used as a first measure. It's only to close that gap. You need to use high quality certified schemes. You need to be aware of double counting, and the optimum approach is to take the leadership approach, where you base your offsetting price on the carbon index, which is currently £70 per tonne. You invest the residual. You pay off offset the residual carbon through the certified scheme at the market price, which is currently somewhere in the region of £12 to £15 per tonne. The remainder of that pot can then be invested in offsetting incubators, which can be more locally focused and foster local sustainable development. So in summary, we need to be gearing retrofit to a whole house approach, and we need to be doing it now. The work that we need to do needs to future-proof to make things last. That includes thinking about when we take out windows and replace boilers. We need to be reducing energy demand through a fabric-first approach, generating energy on site, and ideally storing it as well wherever possible, and then using the offsetting measures to that we need to take to ideally invest in the local communities or national initiatives. And that's me. Thank you.
Great, thank you very much, James. Right, I'll just take control again, and we should be on the right side of the slides. Perfect. Right, okay, so thank you to all of our speakers and to everyone today who has taken time out of their afternoon to join us. So as described at the start of the event, any questions in the chat or conversation box, we will send those to the respective speakers, and we'll post their answers on the CIAT Scotland East Region LinkedIn page. So under the that'll be under the post with the flyer for this event. So this is a relatively new approach for us to try and take the questions away from the away from the video session, the webinar, to the online conversation format. And this is something that will take us a little time to perfect. And we hope that moving the answers online will create a knowledge base and a repository for this topic and allow the conversations around sustainable retrofit methods to expand. So some of the conversations we've been seeing inside the chat have been very much around the different standards, which I think we can all agree are more like methodologies or applications of different techniques and technologies and principles and fundamentals to achieving it. But indeed, the message from our three speakers here today has been something that shows there's lots of opportunities going forward. Also, there is various different approaches and techniques, and not any one of them is going to kind of solve any specific problem, but together, kind of unified as a joint methodology across the industry, there is something that fits almost every archetype. So finally, before I wrap up, I want to say thanks again to LMA Architects, Collective Energy and Collective Architecture for volunteering their time to support this knowledge exchange event today. On behalf of CIAT Scotland East Region and the Scottish Ecological Design Association, we do hope that you have enjoyed this session, and we look forward to seeing you again at our next event on August the 5th, which is a Thursday. And there we'll be launching our Building Performance Methods Knowledge Exchange session. So lots of what was spoken about today from all of our speakers around air tightness testing. We're going to move the discussion towards the new 4 Pascal pulse method for air tightness testing in our next event. So thank you again to everyone who joined us and who took part in the chat and the conversations around different retrofit methods and application of those methods. So until our next event on the 5th of August, goodbye for now, and thanks to all of our speakers.